Hello all, welcome back to our channel, and this time we are going to talk about Common Base Amplifier. This is very important circuit in discrete and integrated design. So as you can see, here is the basic circuit diagram of your BJT employed as common base mode. We call it common base because the base is connected to the ground, and emitter is here where you apply an input voltage, and then you have a collector here. So output is taken from this node, which is collector. And then register RC is its one end is connected to the collector and the other end is tied to the supply voltage. So the input side of the circuit is base to emitter, and the output side of the circuit is collector to emitter, and that is why we call it as a common base amplifier. Before we have seen the common emitter amplifier also, so we can compare the properties about the voltage gain, current gain, input resistance, and the output resistance in these two configuration, that is common emitter and the common base. And there is one more mode called as common collector. So all these three configurations can be compared in terms of open circuit voltage gain, short circuit current gain, input impedance, and the output impedance. Now you see you have the small signal equivalent model of this common base as shown right over here. So the input signal that we are applying to the emitter can be represented by a Thevenin's equivalent. This is Thevenin's equivalent, which is a voltage source along with its series impedance. So Vs represents the Thevenin's voltage and Rs represents the Thevenin's equivalent resistance. So this is how you can model the input voltage that you apply to the emitter of this transistor. Now, with that said, here is your base terminal, and from the base to the emitter, you basically have this resistance R pi that we are going to see. That's the resistance from base to emitter, across which you have a voltage represented as V pi. So here your base and emitter is given, and you need to maintain the transistor in the active region. So base emitter junction is forward bias and the base collector junction is reverse bias. So that's how the condition of maintaining the active mode of a transistor. Now you have this current that is from the collector terminal of the transistor, where you see that the value of this dependent current is Gm times V pi, where V pi is the voltage drop across base emitter junction. So this current is flowing through the resistance RO. RO is an output impedance of your BJT. So here from the collector to the emitter, you basically have a very large output resistance of the transistor. So this current is flowing, giving a drop across it like this. Now, when you draw the small signal AC model, you basically switch off the DC voltage sources. That means they are connected to the ground. That's why the RC one end is connected to the collector here, and another end of the RC is connected to the ground. So this is your input side, that is the external voltage source that you apply, modeled by a Thevenin's equivalent voltage and the Thevenin's equivalent resistance Rs. And this is your an output side, because when you have a draw the output, you are going to connect a load to this transistor to measure the output, to drop the voltage across it. And so RL is connected. Subsequently, your output current IO is going to flow through that resistance, which is modeled here. So with that said, you have this small signal model, and when you look from the output side, into the circuit, there you get the expression for the output impedance or output resistance of the circuit. When you look into the circuit from the input side, you get an expression for the Rin, which is input impedance for AC in terms of AC, or input resistance for a DC. And this is again your base is grounded, which is shown here. Look at the base here is grounded, and this is your emitter, right? So the value of your uh, collector current, which is gm times v pi, right? Now with that understanding, here is how you can get the expression for open circuit voltage gain. So open circuit voltage gain is given as AV, which is the ratio of output voltage by input voltage. So here is the output voltage, and input voltage is what you are applying here. With the RL is infinite, so you take out the RL, which is represented as open circuit, then you only have a RC. With that, you have an expression about GM times RO plus 1 and RC plus RO in the denominator. So usually when you say your GM times RO is very, very greater than 1, so it can be written as GM RO into RC divided by RC plus RO. And with that, RO is generally when RO is very, very greater than RC, because this impedance that we just said RO is greater than this resistance that you connect passively. So therefore, the output expression for the voltage gain is reduced to GM times RC. So remember, in the common emitter mode, for the common emitter mode, we have the gain was equal to GM times RC, the magnitude of the gain. And here also for the common base, your gain is GM times RC. Now you have a short circuit current gain. Short circuit current gain where short you basically short circuit the resistance RL. So RL is equal to 0. And then you have this expression. And in the common base configuration, your current gain is unity, provided you assume the beta of a transistor. Beta is the DC current gain. DC current gain of BJT. You assume that beta is very, very greater than 1. So we have seen in our previous model, beta is usually in the range of 100 to 200. Okay, it can be even larger than that. Third point is input resistance, which is the ratio of input voltage divided by input current, which is this factor here. Remember, the output current divided by the input current, which is the output current here, and the input current here gives you the current gain. Now the input resistance, the expression for which is this one, you basically can reach to this expression by applying the KVL and KCL and Ohm's law to this equivalent model. So with this, your input resistance RE, this is your RE, that is the resistance looking into the input from the input of the circuit, is approximately 1 over GM, where GM is the transconductance of the BJT, which is intrinsic property of BJT, provided you assume this condition, that is output impedance of the BJT, which is this resistance RO, is much, much greater than the parallel combination of RC and RL. Parallel combination of RC and RL, and beta is very, very greater than 1. Now the fourth expression is output resistance, which is the ratio of output voltage divided by negative of the output current. And for that, you assume that the voltage source Vs is short circuited. Okay. Now, and you look from the output side of the from the circuit into the circuit, you look into the circuit from the output side. The expression for the output resistance is this one, and finally you approximately get that RC in parallel with RO, or This is the expression. Again, the condition here is your source impedance is much less than Re, that is the emitter resistance, and your source resistance for the second one is much greater than Re. So this is how you understand the basics of common base amplifier and all the four expression about voltage gain, current gain, input impedance and output impedance, and you also know how to understand the small signal model. Now we move to the second part of this. Let me take you there. Now the amplifier's input impedance, which is Rin, where we are looking into the emitter node, we are basically looking into the emitter node, is very low, which is given by this expression, which is Rin is equal to Re, small re, divided by Vt over Ie. So Vt is the thermal voltage, which is 25 millivolt at the room temperature. I is the DC current, DC emitter current value. Okay, so if we assume that I have 25 millivolt of Vt and the value of IE is, let's say, 10 milliampere, so R in that case is about just 2.6 ohm. So it's very low, as I said. In case of a common emitter amplifier, if you recall, R in was equal to R pi about Vt over Ib. So Vt was again thermal voltage, but Ib was the base current, which is usually in the range of 10 microampere. For example, uh, it was in the range of microampere. So if we assume 10 microampere Ib and the Vt about 25 millivolts, so it is in the kilo ohms. So if you see the input impedance of your common emitter amplifier is 2 to 3 orders larger than the input impedance of your common base amplifier. So now here, coming back to here, if you reduce the value of IE in order to increase your R in, there are some consequences, like your transconductance, that is GM, drops, your output resistance increases, and your beta also goes down. So these things you need to consider. So the practical solution to this low input impedance problem is to place the common emitter stage at the input to form a cascade amplifier. So you have this input voltage that is coming right here. So the first amplifier that you place here is common emitter stage, and then second amplifier that you place is your common base. So common emitter have R in is larger, and then here the common base you have R in is lower, and the common emitter has output resistance RO, which is lower. So here is a match, right? And then this is how you can use. So this kind of configuration is called as cascade configuration. Okay, so we continue to talk about that. We have seen that. So now, since the input impedance is lower, most signal sources have large source impedance than the common base amplifier. So as you can see right here, your a common base equivalent circuit, whether this circuit or the model, is being driven by this external signal source with the value Vs, and it has its own impedance Rs. So usually Rs is greater than Rin. So Rin is very small. We just saw that it is 2.6 ohm for a given values of Vt and the DC emitter current. So your Rs is usually 10 ohm, and which is greater than 2.6 ohm, right? So because of this, your source delivers a current to the input rather than uh, delivers a current to the input rather than a voltage, even if it is a voltage source. So when we are saying that we have connected a voltage source with the equivalent resistance, series resistance Rs, and it is delivering the current actually, which is called as I1. So we basically say that your common emitter amplifier receives the input current I, even if we are feeding it with the voltage. Okay, so this effect can be modeled with Norton's equivalent. So Norton's equivalent is like a current source in parallel with a resistance. That is a dual of the Thevenin's equivalent, which is a voltage source in series with resistance. So the value of this I in is given as Vs divided by Rs. So this current value I in here, let me just clean this. Now this I1 or Is is called as Vs divided by Rs. That is the value of it. So if the output signal is also a current now, if you take that, so obviously you can say that your amplifier is a current buffer with a ratio of the currents divided output current divided by the input current. So output current is equal to input current equal to IO is equal to IS. So this is called as current buffer. So we see that your common base amplifier acts as a current buffer and it delivers the same current as the input current. But if your output is taken as voltage, for example, you have the output voltage here. The amplifier then is called as VO divided by R, IS. So it is called as Transimpedance Amplifier and it delivers output voltage depending on the load impedance. Whatever the load impedance you have, based on that, it delivers the output voltage. So your output voltage in this case would be written as U will be I in times RL. Okay. And I in or IS and I in are same. Okay. And this is how you have this one. So here we see that the expression VO V output equal to I in times RL, and you can write that I in is your Vs divided by Rs. We just wrote that I in is Vs divided by Rs multiplied by RL, and your gain is V output by Vs, which is your RL divided by Rs. So now you can see that the gain here is just set by the resistors ratio RL divided by Rs. In a common emitter configuration also, the gain is the same. So the voltage gain in common emitter and the common base is same. That is how, that is, we set this by means of resistors ratio. Now we move forward and we say that for a special case of very low impedance sources, this common base amplifier does work as a voltage amplifier. So what we just discussed now. So here we assume that uh, your gain, for example, the voltage gain, which is the ratio of output voltage divided by the source voltage, can also be written as load resistance RL divided by small re, and re, and then finally it can be written as GM times RL. So same as common emitter amplifier. So here GM is your DC collector current divided by the thermal voltage is the transconductance. And we note here that the source impedance, for if the source impedance Rs is low, then your R out will be a parallel combination of RO in parallel with RC. Now finally, we would now take a look at common base mode transistor as a current follower, what we just said. So here is a small signal model for that. Here is your base terminal, this is your collector terminal, and here is your emitter terminal. And this is your IS times RS IS is your VS by RS, and this is your Norton's current source. So we basically feeding the emitter of the transistor with the current source. And then you have this resistance R pi. Here is your voltage at the emitter, and then you have this current. This current is actually flowing to the resistor like this, developing a drop across it, and then this current is also flowing through the resistor RL. Okay, so we say that the output current RL is equal to IS, that is the input current. In this case, the output resistance is large. Even in the worst case, it is at least RO in parallel with RC, and can become beta plus 1 into RO in parallel with RC for large RS. And large output resistance for a current follower is desirable. And current gain, as I said, is equal to 1. So hope you found this video useful regarding common base amplifier. We've seen that how it also compares with common emitter, and we continue our discussion with that.